Early internetworking architecture relied on monolithic, flat broadcast domains. Every device connected to the network shared a single continuous logical space, meaning a signal sent by one machine reached every other machine on the hardware. That open design creates an immense vulnerability. In a flat network, a single compromised endpoint provides unrestricted lateral access. An attacker or a self-propagating piece of malware can scan, pivot, and infect thousands of machines because there are no internal boundaries to constrain the blast radius. When attackers breached the Colonial Pipeline in 2021, the lack of rigid segmentation between their corporate IT network and their operational technology systems allowed the ransomware to spread across the entire infrastructure, forcing a massive systemic shutdown of fuel distribution. Network architects solve this structural vulnerability by operating at layer 3 of the OSI model. Using the Internet Protocol Suite, they implement a process called subnetting. Subnetting is the mathematical process of borrowing bits from the host portion of an IP address and reassigning them to the network portion. This splits a single large broadcast domain into multiple smaller, logically isolated partitions. By isolating traffic, these partitions dictate the trust relationships between different limits. A finance department handling sensitive payroll data and a public guest Wi-Fi segment can exist on the exact same physical wiring, yet remain completely invisible to each other. Subnetting serves as the network's structural foundation. It is the mathematical mechanism architects use to optimize routing performance and enforce tactical security containment. To understand how these boundaries are drawn, we have to look past the human-readable dotted decimal format. This diagram shows an IPv4 address in its true hardware-level architecture, a string of 32 binary digits separated into 4 8-bit blocks known as octets. Every bit in an octet carries a specific positional weight based on powers of 2. Reading from left to right, the values drop from 128 down to 64, 32, 16, 8, 4, 2, and 1. If all 8 bits are set to 1, their sum equals the maximum decimal value of 255. To determine exactly where the network identifier ends and the individual host identifier begins, devices use a Subnet Mask. This is a second 32-bit filter made entirely of contiguous ones followed by contiguous zeros. Hardware processes this filter using a bitwise Boolean AND operation. The logic is absolute. If both the IP address bit and the corresponding subnet mask bit are 1, the resulting output is 1. Any other combination outputs a 0. Watch the scanning line apply this logic to the IP address 192.168.1.132 using a standard subnet mask of 255.255.255.0. The zeros in the final octet of the mask cancel out the host value of 132. The resulting output completely isolates the network portion of the address, 192.168.1.0. This deterministic binary math occurs at line speed for every data packet. It is the physical baseline allowing any device to instantly recognize exactly where its local network ends. When an architect wants to create smaller segments, they must borrow bits from a host portion and assign them to the network mask. This introduces a strict trade-off. You gain a higher volume of isolated subnets, but mathematically reduce the capacity of hosts within each one. This transformation relies on 2 equations shown here. The total number of new subnets created is 2 to the power of n, where n is the number of borrowed bits. The usable host addresses per subnet is 2 to the power of h minus 2, where h is the remaining host bits. Subtracting 2 is a permanent rule of IP architecture. Every single subnet must reserve 2 addresses for operational functions, the network address, where all host bits are set to 0, and the broadcast address, where all host bits are set to 1. Consider an organization assigned the network block 172.16.100.0 with a default /24 mask. If they need to physically separate multiple departments, each requiring exactly 14 hosts, they must calculate a custom boundary. Plugging 14 into the host equation reveals that exactly 4 bits must be retained. 2 to the power of 4 is 16. Subtract the network and broadcast addresses, and we get exactly 14 usable hosts. Because 4 bits were kept for the hosts, the remaining 4 bits from that final octet are surrendered to the network. The Subnet Mask prefix extends from /24 to /28. Those 4 borrowed network bits read as 11110000 in binary. Applying positional weight, 128 plus 64 plus 32 plus 16, gives us a new decimal subnet mask of 255.255.255.240. The network block has now been fractured. The new subnets will increment sequentially at strict boundaries, 172.16.100.0, then .16, then .32, continuing upward. Calculating specific subnets guarantees that multiple isolated organizational groups can be tightly packed onto the same physical hardware without their address spaces colliding. Before sending data, a computer compares its own network ID against the destination's network ID. If the binary matches, the target is local. If the binary differs, the destination is remote, and the traffic must be routed. To reach a remote network, a computer must forward its packets to a default gateway, typically a local router that acts as the doorway to the outside world. Network protocols require the default gateway to reside within the exact same logical subnet as the host machine. The reason for this rule is found at layer 2 of the OSI model. As this animation shows, an IP packet moving across a physical wire must be encapsulated inside an Ethernet frame. To build that frame, the host needs the specific physical MAC address of the default gateway. To discover that MAC address, the host sends out an Address Resolution Protocol, or ARP, broadcast over the local network, asking the gateway to identify itself. Imagine a system administrator assigns a computer the IP address 192.168.1.10 with a /26 subnet mask, but accidentally configures the gateway as 192.168.1.129. A /26 mask strictly limits that host's subnet boundary to .63. The assigned gateway of .129 exists in a completely different logical segment. Routers are designed to block layer 2 broadcasts. When the host sends its ARP request searching for .129, the signal hits the /26 subnet boundary and drops. The MAC address is never resolved. An out-of-bounds gateway assignment causes a physical encapsulation failure. The host remains permanently isolated, unable to resolve the hardware addresses required to leave its subnet. Smaller broadcast domains impose physical constraints on the potential blast radius of an active attack. This shift transforms routing logic into a tactical security asset. Strict subnet boundaries are the foundation of a zero-trust security model. By explicitly denying lateral traffic between segments, attackers are forced to bypass dedicated firewalls rather than simply sliding across an open switch. Without these boundaries, entire protocols can be weaponized. A Smurf attack is a denial-of-service maneuver that targets the IP broadcast address. An attacker sends an echo request, a ping, to a network's broadcast IP, but spoofs the source data to look like it came from the intended victim. Look at what happens in an unsegmented /16 environment. A single spoofed packet hits the broadcast address, and all 65,000 hosts simultaneously reply to the victim, creating a massive amplification effect that crushes the target's bandwidth. In the segmented /28 subnet we calculated earlier, that exact same attack is structurally contained. The broadcast stops at the subnet boundary, limiting the maximum possible amplification to just 14 replies. This identical principle neutralizes DHCP starvation attacks. By segmenting discovery domains, an attacker flooding the network with fake MAC addresses can only exhaust the tiny IP pool of their local subnet, leaving the rest of the enterprise fully functional. Subnetting mathematically limits the resources available to an attacker. A smaller broadcast domain physically chokes malicious amplification before it can escalate. As enterprise infrastructure migrates to platforms like AWS and Azure, the physical hardware disappears, but the binary principles remain. This isometric diagram shows a modern virtual private cloud, governed entirely by the exact same CIDR notation blocks. Cloud architectures use software-defined networking to partition the VPC into logical subnets, enforcing routing and broadcast rules through code rather than physical routers. In these environments, subnets are paired with security groups, a mechanism that achieves micro-segmentation by acting as a distributed instance-level firewall for individual virtual machines. As the industry adopts IPv6, the sheer volume of available addresses eliminates the problem of IP scarcity. Yet CIDR subnet boundaries are still rigidly applied, driven entirely by the need for strict management and security logic. Layering subnets with access controls creates a prevention-first strategy. Architects can calculate and constrain the theoretical blast radius of a breach before a single server is ever deployed. The process of shifting a 32-bit string of ones and zeros physically dictates both the routing pathways of data and the perimeter of an organization's security. Subnetting provides structural immunity. Mastering the deterministic logic of Layer 3 isolation allows network professionals to build resilient, tiered infrastructure that can physically contain the expanding threat landscape.